All right, can you see my Canvas calendar?
Yes.
All right. Today is August 23rd. So we're going to go over chapter 1 and chapter 2. There are few slides I need to go over in chapter 1. Then I'm going to start chapter 2 slides. Okay. So our it's going to be on September 13. All right. Okay. I'm going to go to slide, PowerPoint slide here. Can you see it, specific gravity?
Yes.
Okay.
Yes.
We go over this. I think we need to start from, let me see, about energy. We're going to start energy right today. Excuse me. Energy is defined as capacity to do work. Energy is shown by moving object or known as kinetic energy. If an object made out of matter moves, it has kinetic energy. Another form of energy which are common to matter is potential energy. Potential energy is energy an object made out of matter has because of its position. A rock on the bottom of a hill has lower potential energy than the rock on the top of the hill. Rock can fall down and release energy. That energy is potential energy. Moving object has energy. It's called kinetic energy. Kinetic energy is calculated by multiplying its mass times velocity squared. 1/2 of 1/2 mass velocity squared. So as the velocity increased, kinetic energy increased. As the mass increased, also the kinetic energy increased. Now these are the two forms of energy which is common that's seen in the matter. Objects are made out of matter. We talked about matter. Matter is something that has mass and take up space. Example of kinetic energy is mechanical energy. Mechanical energy is when a car moves along the road. That is a mechanical energy. You can move certain weight, certain mass in the car, certain weight, certain people in the car. From the mechanical energy created by the machine, internal combustion engine in the car. Light also is a form of kinetic energy. Light is considered very small, very, very small particles of matter moving at a certain velocity, which is velocity of light. So depending on the particle size, they have different colors. So heat is also a kinetic energy. Heat is due to kinetic energy of particles making out of matter. Particles move faster, more heat it has, or temperature is higher. Heat temperature is an indicator for amount of heat. Higher the temperature, heat is most. Lower the temperature, lowest heat. Also, electrical energy is also a form of kinetic energy. Electrical energy is fast moving electrons to a conductor. When you apply the potential, electric potential, the electrons flow from negative end to positive end. A current is passing through positive end to negative end. You probably heard about that. Therefore, energy, mechanical energy, light energy, heat energy, and electric energy are kinetic energy. Kinetic energy. Can someone turn off his mic or her mic? I hear some noise in the background. If you need to ask a question, you can turn on and ask, okay? In chemistry, most of the important forms of energy is potential energy. Also, atoms have chemical energy or nuclear energy. Chemical energy is energy in the chemical bonds. It's like a potential energy due to the placement of atoms in a bond. It has certain energy. Bonds need to be broken by providing energy. Potential energy is a form of potential energy. Nuclear energy is produced in nuclear reactions where nuclei break up, losing mass of nuclei. Enormous amount of potential energy is released during a nuclear reaction. Chemical energy stored in substances are used in energy production for our day-to-day things by burning carbohydrates, fats as we eat our food. Stored chemical energy is the main source of energy that we use to do our daily routines. Chemical energy is a potential energy that is given off in a chemical reaction. If you burn carbon with oxygen, it produces carbon dioxide and energy. One of the important thing about energy is it follows law of conservation of energy. Energy neither be created nor destroyed is the law of conservation of energy. That means energy is already here. Only we can convert one energy from one form to another. All right? So this law of conservation of energy is called first law of thermodynamics. What is first law of thermodynamics? It is the law of conservation of energy. Energy is neither created nor destroyed. One form of energy that is important for us is heat. Heat is related to temperature. Heat is transferred from hot object to a cold object. Therefore, temperature is the one that decides which way the heat energy is transferred from an object. Heat energy is in the atoms and molecules and ions making up the matter, piece of object, which is made out of matter. Those particles, atoms, molecules, ions, move faster as we heat the substance or the matter. Heat energy always flows from hotter object to cooler object until they achieve same temperature. They reach same temperature. Heat is normally measured in calories. If someone asks you, what is a calorie? What would you say? It is the heat required to raise the temperature of 1 gram of liquid by 1 degree Celsius. It's exactly 1.00 calories. Calorie is not a part of SI units. SI unit is where kilograms, liters, Kelvin, those we talked about. That's unit 6 base units. Heat is expressed in joules, not in calories. But we normally measure heat in calories in normal work. But in scientific work, heat is measured by joule. 1 calorie is 4.184 joules, or 1/4 of a calorie is equal to 1 joule, roughly about 1/4 of calorie is equal to 1 joule. Heat absorbed by 1 gram of any material to increase temperature by 1 degree Celsius is called the specific heat of that substance. In the previous slide, we defined calorie as a specific heat of water. In the table, specific heat of water is 1. Units of specific heat is calories per gram per centigrade Celsius. So that means heat required by 1 gram of material to increase the temperature by 1 degree Celsius. If you look at the specific heat of various different substances, they are quite different. Water has the highest specific heat. You would imagine copper, lead, metals might have larger specific heat. They don't. Water is the one that absorbs most heat per gram to increase the temperature by 1 degree Celsius. So the specific heat is a physical property of a substance or pure substance, elements or compounds. So we can identify, if we know the specific heat of a substance, what that substance would be. We can find out. So we do also calculate heat absorbed by certain material, substance, using specific heat, which I'm going to show in the next slide here. The following equation gives the relationship between specific heat and amount of heat and the mass of an object, and also using temperature change. SH means specific heat. Small m means mass. Big T2 minus big T1. Big T is the temperature. T1 is the initial temperature. T2 is the final temperature. If you have a problem like shown below, an example, you are asked to calculate how many calories are required to heat 350 grams of water from 23 to 95, and the specific heat of water is given 1.00 calorie per gram per Celsius degree. Now, if you look at this, in equation is HS, specific heat times mass, T2 minus T1. So T2 is final temperature. T1 is initial temperature. So specific heat is written down to calculate the amount of heat times 352 grams. In the problem, mass of water is 352. Then I substitute T1, 23, and T2, 95, because water increased the temperature of the water from 23 to 95. So when I do that, I get 2.5 10 to the fourth, or calories converted to kilocalories divided by 1,000. So I get 25 kilocalories. So we can convert this to joules using the conversion factor. 1 calorie is equal to 4.184 joules. In this case, we leave it at calories, kilocalories. Now we go on over certain aspect of energy. Now, in previous slides, we talked about states of matter, scientific method, measurement, properties of a measurement, number part, unit part. So I am going to finish the chapter 1 now and move into chapter 2. I am going to close the chapter 1 slide and move on to chapter. Let me go and, that's the first web page for this chapter 2, Adam.
We see
You can, yeah. So we go now classifying matter, and what is in the Dalton atomic theory, first atomic theory to describe the matter composed of atoms. And we went over composition of atoms, protons, neutrons, electrons, and we started the periodic table. We gone over periodic table in detail, the column structure, group structure, periods, element types, classification of elements, metal, non-metals, metalloids. There are so many ways to describe the elements in the periodic table. Transition metals, inner transition metals. Inner transition metals are the lanthanide and actinide at the bottom of the two rows at the bottom of the periodic table. First row is called lanthanide. Second row is called the actinide. So we went over group numbers 1 through 18, and there is second way to number the groups like 1A, 2A, like that. So if you have a copy of periodic table, you can see that. Periodic table shows classification of elements according to their chemical properties and atomic number. Atomic number is number of protons in a nucleus of an atom of an element. So these details of atom, we go over atomic sizes and what is in the nucleus, etc. The electron arrangement in atoms are important. Chemistry depends on electrons of atoms. Chemistry mainly involves redistribution of electrons. Chemical reactions are mainly bond formation and things like that. To describe that chemical reactivity, we had to know how the electrons are arranged in an atom. So that's what we describe using periodic table. Periodic table has basically structured the atom. Atom with respect to electrons. We don't worry about nucleus in the periodic table. Nuclei are stable, they don't change. So electron behavior change in chemical reactions. Periodic table is basically electronic structure of atoms. There are periods. We also call them shells. There are 7 periods in the periodic table. We call them shells. The first period is the lowest energy shell, and the 7th period is the highest energy shell. So shell is like a size of the electron. As the shell number increase, the electron size, electron distribution around the nucleus increase.
Hey, Professor, the slide is still stuck on number. Thank you, sorry.
No problem, I understand. I'm going to go through, I'm taking this little bit slowly. I don't want to jump into one page and just go through them, okay? I'm going to go through. What I'm trying to say is this. Periodic table is the roadmap for electron arrangement. Okay, shell structure, subshell structure. Subshells are electronic shape called atomic orbitals. Each shell has SPDF subshells. Okay, so when we fill electrons into atomic orbitals, and atomic orbitals can hold 2 electrons. I'm going to show you in a minute. And then we keep filling electrons to lowest energy shells first, then go to next shell until we run out of the electrons. So electron configuration and periodic table is important. Okay, let me start where I left off.
Yes, I see evidence for Dalton's theory. Is that what we're supposed to be on?
Yeah.
Okay.
Let me go back. I'm sorry about this. Chemicals, ordinary things are chemicals. Now you see it. Can you see it?
Yes.
Okay, I'm glad you told me because I was sharing the other slide. So it didn't go to the chapter 2. Okay. So this is the one we talked about. This guy came up with the idea, all things are made out of atoms. All right. Evidence for Dalton's atomic theory. The evidence comes from 3 chemical laws. Law of conservation of mass during a chemical reaction. Law of constant proportions, we're going to talk about, and law of multiple proportion. There are 3 chemical laws that he observed during a chemical reaction, a pattern in the observation. First one is law of conservation of mass. In a chemical reaction, mass of the reactants are equal to mass of products. Mass is conserved. It's like energy is conserved. Energy is neither created nor destroyed. We are not talking about energy now. We are talking about matter. He explained, if matter is made up of indestructible atoms, then any chemical reaction just change the arrangement of atoms or the bonds between atoms. But chemical reaction does not destroy the atoms. Therefore, chemical reaction is rearrangement of bonds. Bonds are broken, new bonds are formed, but the atoms remain the same. Okay? So, for example, if you react carbon monoxide with lead oxide, lead oxide is converted to lead. Carbon monoxide is converted to carbon dioxide. The mass of carbon monoxide and lead oxide is same mass as carbon dioxide plus lead produced. Dalton's also observed as evidence law of constant proportions. These laws came out doing many chemical reactions. a pattern in chemical reaction. This statement shows when two elements combine to form a compound, the elements that combine have fixed constant proportion. The ratio between masses of two elements are always same. This law is given by Joseph Proust initially. Now Dalton explains this law. If you take 36 grams of water, it has 4 grams of hydrogen and 32 grams of oxygen. How do you produce water? Is you combine hydrogen and oxygen. So water is always has this constant proportion, 4 grams to 32 grams. Or simple proportion is 1 to 4. How do I get 1 to 4 from 4 to 32? 4 divided by 4 is 1, 32 divided by 4 is 32 divided by 4 is 8, right? 1 to 8. 1 to 8. The exact same proportion of hydrogen and oxygen by mass must always be found in water that is present in everywhere. Water is a compound, it has constant proportion of elements that are making up water in 1 to 8 ratio. Now, atomically, hydrogen and oxygen combines to form water as given here. So this idea, constant proportion, explains the atoms combine to form compounds, elements combine to form compounds. Now the third evidence comes from, ultimately gives law of multiple proportion. That means, multiple proportion means, when two elements combine, they could form two different compounds. Water is a H2O. Water is also possible to form hydrogen peroxide. H2O2 is hydrogen peroxide. So carbon and oxygen also can produce carbon monoxide, CO, or carbon dioxide. When two elements combine, two different combine through. You have a question? Can you see the slide?
Yes.
Okay, let me check it. When two different elements combine in whole number, multiple ratio, they form two different compounds. For example, carbon and oxygen combine to form carbon dioxide, carbon monoxide, and carbon dioxide. If you take 12 grams of carbon, it can react with 16 grams, would give carbon monoxide, CO. 12 grams with 2 times 16, that's the multiple proportion. The second element, simple ratio is 1 to 2. Between first compound, CO and CO2, the multiple proportion is 1 to 2. 16 divided by 16 is 1. 32 divided by 16 is 2. 1 to 2. So that explains when two different elements combine, if there are multiple proportions, various two different compounds are formed. In the picture, carbon react with oxygen, one atom each. That is 1 to 1. In the second one, the multiple proportion is 1 to 2 from first reaction to produce carbon monoxide and second reaction to produce carbon dioxide. 1 to 2 multiple proportion. So these indicate that when compounds are formed and multiple compounds are formed from two different elements, it goes along with the idea. Atoms are the basic component of matter. So Dalton came up with the idea to explain conservation of mass. Atoms cannot be destroyed. All matter composed of tiny particles called atoms. That's the idea that he came up with. All atoms of the cell elements have same chemical properties. Atoms of different elements have different chemical properties. Now, we have about 180 in the periodic table, different elements. So one element has same properties for all the atoms. Different elements have different properties, chemical properties. He also explained the second evidence or definite proportion, constant proportion. The idea that compounds are formed from combination of two or more atoms of different kinds. They have constant proportion. Water has 1 to 8 constant proportion between hydrogen and oxygen. He also came up with the idea compounds could contain 2 or more atoms that act as a single unit. We call them group of atoms bonded to each other. It's called a molecule. Now, do you see that how we came up with the idea about atoms, molecules, and ions from Dalton's atomic theory? All matter is made out of atoms, compounds, and molecules. When you look at the atomic view, Some of them are monoatomic. Some elements contain only one type of atom. Some of them have diatomic molecules, like oxygen, hydrogen, and others have polyatomic molecules. If you look at the periodic table, the last column on the right is called noble gases: helium, neon, argon, xenon, krypton, radon. They are monoatomic. These elements of noble gases have only one kind of atom. Some of them have, some other elements have diatomic. Example of them are these gases. 7 gases exist as diatomic molecules, diatomic particles or molecules. Molecule is a group of atoms. There are 2 in there, it's called diatomic. Polyatomic molecules containing elements containing polyatomic molecules. Ozone has 3 oxygen atoms. Phosphorus has 4. Sulfur has 8. Carbon in the form of diamond has large number of carbon atoms, millions of carbon atoms bonded together to form gigantic cluster, very large diamond crystal. It's made out of millions of carbon atoms. So we're going to look at the picture and understand that we can look at certain things in 2 ways. We can look at matter macroscopically, as we see it with our eye, or we can use our mind's eye, atomic view of matter. This soft drink glass, as you see it, you see the brown liquid in the glass. It's just a brown liquid, macroscopic view. But in the mind's view, atomic view, or atomic molecular view, it's composed of water. Water is H2O molecules. Can you see them in the picture? They are in the circle right here. Carbon dioxide, that's the gas that releases when you open up a bottle, soft drink bottle. This unit with the blue and black balls is the glucose. No, I'm sorry, this is the glucose here in the bottom. And this one is a coloring material. There are certain substances that use colors to water. So they're shown in the molecular view or atomic view. That's the mind's view. If you look at the tip of the pencil here, it's made out of carbon, graphite. When you write with a pen, the graphite leaves a footprint where the pencil were. Some of the atoms are transferred onto the paper. When you look at this hand of the person writing using the pen, hand is made out of proteins. Proteins are molecules of amino acids. So that's our view. Atomic view of matter is a chemistry or the scientist's view of matter. Chemistry is not only used by chemists. but many other areas, medical fields, engineering, and in fields of engineering, chemistry is used with the atomic view of matter. To tie up classification of matter now, all matter is anything that has a mass and take up space. Matter is pure substances or mixtures. We talked about that. Mixtures are combination of pure substances. You can separate mixtures into pure substances. Pure substances cannot be physically separated. Pure substances are elements and compounds. Elements combine chemically to form compounds like hydrogen, oxygen to water compound. So pure compounds, substances are elements and compounds. Mixtures could be heterogeneous or homogeneous. Homogeneous mixtures have uniform composition. Heterogeneous mixtures have non-uniform. Different part of the sample have different composition, non-uniform. So if you knew the physical properties of mixture, making up the mixture, you can use a separation method to physically separate mixture into pure substances. For example, water and alcohol. Since alcohol has lower boiling point, you can boil alcohol mixture, excuse me, or alcohol mixture distill to produce, separate alcohol from water. That's done in after fermentation of glucose or sucrose. That is converted into alcohol by fermentation. You can separate alcohol from water. Now we're going to look into classification of matter into elements. Most simple matter is elements. Elements are made out of one type of atom, carbon, hydrogen, iron. There are 118 known elements in the periodic table. We're going to look into this in a minute. They have a different structure of the atom. Out of these 118, 98 elements are found in nature. Rest, other about 20, are radioactive. They have decayed, but they could be made in the lab by physicists or chemists. Some new elements are synthesized artificially in accelerators. Each element in the periodic table has a symbol, consists of one or two letters. For example, hydrogen, atomic symbol for the element is H. How do you get H for hydrogen? you use the first letter, which is H for hydrogen. Helium is, atomic symbol is for helium is He. Since we use hydrogen for H for hydrogen, helium cannot be H. So you pick up the second letter, which is written in small case. First letter is big case, big letter. Second letter for an element, if we have, is a small case, helium. So most of the elements have atomic symbols taken from English name. But there are about 20 elements in the periodic table, which has symbols taken from different languages. For example, sodium is not SO, sodium is Na, because the name of the sodium was given in Latin, kalium. Sodium is given in natrium, Na. Potassium is K. Name of the potassium is initially given in Latin, kalium. K is picked up for that. Therefore, you have to look at the different elements in the periodic table or list of element names and their symbols and find out what they are and the name. For example, pick up elements like Fe, element symbol Fe is iron. Why is iron is ION is not the Fe? Iron name comes from ferrum. Ferrum is Latin name. Iron is called ferrum, Fe. So you have to go through the about 20 elements which have names coming from other languages when they were given. The names are derived from variety of sources. English name for element. People important in atomic science. Mendeleev is the one came up with periodic table. Geographic locations, California, planets, uranium, metallurgical sources. I don't have an example for that, metallurgical. So you find out. Origin is not very important right now. Atoms have names from original names used when they are discovered. So we talk about elements. Now we talk about compounds. A pure compound or pure substance is a compound when it is made from two or more elements, obeying law of constant proportion. They have fixed ratio by mass, like water has 1:8 mass ratio. Unlike atoms have symbols, one symbol. Formula of a compound has more than two symbols. The number after the atomic elemental symbol shows how many atoms are in the formula. Sodium chloride is a formula of sodium chloride. Ratio is 1:1. Water is H2O. There are 2 hydrogen atoms per 1 oxygen atom. 2:1, 1:1. So formula tells how many atoms in the molecule or the compound. A water molecule could be represented by molecular formula, which is water. Structural formula that shows the bond. Ball and stick model, which is pictorially showing the attachment of oxygen red balls to gray balls, hydrogen. The space filling model shows distribution of electrons in the atom. So this is something, space filling model is more closer to real water molecule than other 3. There are 3 forms of representation that we're going to look at when we talk about chemistry examples. When you are going through examples, we will use 4 different representations for molecules. Now the mixture is a mixture of pure substances. 2 different elements. One element and another combination of 2 or more pure substances. Pure substances are elements or compounds. So you can have 2 different elements mixture, 2 or more elements, or 2 or more elements and a compound combinations like that. Substance may be present in any mass ratio. In a mixture, there's no constant composition between constant ratio. When you make heterogeneous mixture, homogeneous mixture of salt water, salt dissolved in water, you can dissolve little amount of sodium chloride in water, get a dilute solution. Dilute means less concentrated, or you can produce more concentrated solution. These are the language we use for showing mixtures. Dilute solution, concentrated solution. Each substance has a different set of physical properties. So physical properties of the mixture depend on composition. When you add more water, it becomes more like water, but properties are a little different than pure water. When you add a lot of sodium chloride, it would be a little different from pure water. Okay? So properties of mixture depend on component ratio, mass ratio of the component. Mixtures be homogeneous or heterogeneous. Homogeneous means uniform composition throughout the sample. Heterogeneous means non-uniform. If we know the physical properties of individual components of the mixture, we can use appropriate physical means, separate the mixture into its component parts. We talked about this. We talked about alcohol water mixture. If you know boiling point of water is higher than boiling point of alcohol, you can heat alcohol mixture to the boiling point of alcohol, which is about 85, and distill of alcohol from the water and separate, get more concentrated alcohol. That's distillation. When you know the properties of components, we can separate. I am going to talk about structure of the atom. It's 2:37 now. I'm going to stop at this point. Okay? We started at 1:30, right? Okay, you guys there?
Yes.
We're going to meet on Thursday, okay? And talk about subatomic particles. All right?
Okay.
Just read chapter 2 and look at some problems in the sample questions and answers, okay? All right. I'm going to see you the next Thursday, right?
Yes.